Swayam Prabha. Digital India. Educated India.
Welcome to lecture 8. We'll continue with the numerical problem pertaining to vapor compression refrigeration cycle. In this lecture, I will be solving a problem in which both subcooling and superheating is involved. So let us go to the problem. A refrigerator uses R134A as the working fluid and operates on an ideal vapor compression refrigeration cycle between minus 18 and 32 degrees centigrade. So the evaporator and the condenser temperature remains the same like the previous cases. The refrigerant is superheated to minus 10 degrees centigrade. The refrigerant is superheated to minus 10 degrees centigrade at the inlet of the compressor. So we have solved this particular case separately, and also the refrigerant is subcooled. Refrigerant is subcooled in the condenser to 26 degrees centigrade before it is throttled. So separately we have seen the performance of a vapor compression system in which the refrigerant is superheated at the inlet of the compressor, and in the previous lecture we have seen the condition of refrigerant, liquid refrigerant leaving the condenser. It is subcooled from 32 degrees centigrade to 26 degrees centigrade. So this problem is a combination of both subcooling and superheating. The flow rate of the refrigerant remains the same, 0.05 kg per second. Determine the rate of heat removal from the refrigerated space and power input to the compressor, rate of heat rejection to the environment, and COP of the refrigerator. So let us first draw the TS and PV diagram. So let us draw the TS diagram first. Temperature entropy diagram. Refrigerant is superheated at the inlet of the compressor. So this is state point 1, isentropic compression 1 to 2. Heat rejection process. This is 2 dash. This will be 1 dash. And first let me draw without subcooling. So this will be a line perpendicular to y-axis. So this is process 3 to 4 without subcooling. 1 to 2 is isentropic compression, work of compression. This is heat rejection process, QC. This is evaporation. And subcooling is there. So let us represent the subcooling by a dotted line. So this is 3 dash. This is 4 dash. This is 3 dash, this is 4 dash. Let us mark the temperatures on the y-axis. So this will be evaporator temperature. This is evaporator temperature TE minus 18 degrees centigrade. This is condenser temperature 32 degrees centigrade. T3 dash is given. That is, the refrigerant is subcooled from 32 to 26 degrees centigrade. The degree of subcooling is 6 degrees centigrade. So T3 dash is equal to 26 degrees centigrade. We don't know the temperature of T2, temperature of the refrigerant after it is compressed, and this is also given. T1 is given. The refrigerant is superheated to minus 10 degrees centigrade. So let me, T1 is equal to minus 10 degree centigrade. So apart from evaporator and condenser temperature, two more temperatures are given. One is temperature of the refrigerant after it is superheated at the inlet of the compressor, that is T1. This is also given, and this is also given. T3 dash is also given. This is also given. Let me plot the pH diagram. So this is superheated condition 1 to 2. This is 1 dash. This will be 2 dash. This will be 3. And this will be extended. This is without subcooling. And the dotted portion, this is 3 dash. 3 to 4 is throttling process without considering subcooling, and this is 4 dash. This is 4 dash. So this is evaporator heat load, condenser heat load, work of compression. Work of compression. Let us write this point here. This point is, okay, let 1 dash. Let us write the given data. Evaporator mass flow of the refrigerant is given as 0.05 kg per second. Evaporator temperature is equal to, see, 1 dash, 4 dash are all same temperature, are lying the same. So T1 dash equal to T4 equal to minus 18 degrees centigrade. Condenser temperature is equal to 2 dash and 3 are same, all lying in the same line, isothermal line. 2 dash 32 degrees centigrade. Temperature at state point 1 is given. T1 is equal to minus 10 degrees centigrade. Similarly, temperature of the after subcooling is given. T3 dash is equal to 26 degree centigrade. 26 degree centigrade. I think 4 temperatures are given and 1 mass flow rate. Okay, let us solve this problem. Let us take state 1. State 1. First, we can find out enthalpy at 1 dash, enthalpy at 2 dash. All these points are lying on the saturated vapor line. Let us take state 1 dash. State 1. State 1 is superheated enthalpy is equal to saturated enthalpy plus Cp of vapor into delta T. Delta T is, I am finding the enthalpy at state point 1. It is superheated condition. So saturated enthalpy is 1 dash plus Cp of vapor into delta T. T1 minus T1 dash. T1 minus T1 dash. T1 dash. So here H1 dash is equal to, let us first find out the average temperature, where Cp of vapor is to be evaluated at average temperature of T1 and T1 dash by 2. Since both the temperatures are known, So T1 is minus 10, T1 dash is minus 18 divided by 2. So that is equal to minus 14 degree centigrade. So that is what I have written here. Cp of vapor is at minus 14. Cp of vapor have to be evaluated. Cp of vapor. So let us go to the table. Minus 14 is here. Cp of vapor is the last column, 0.827. So Cp of vapor equal to 0.827 kilojoule per kg Kelvin from R134A table at a temperature of minus 14. Now, if we find H1 dash, we can find enthalpy at H1. H1 dash is like 0.1 dash is lying on the saturated vapor line. So it is saturated vapor enthalpy at temperature T1 dash. T1 dash is minus 18 degrees centigrade. So that means H1 dash is equal to the value of H1 dash corresponding to minus 18 degrees centigrade from the table. That is vapor enthalpy 387.89. 387.89 kilojoule per kg from R134A. 387. So here you can see H1 is 387.89. H1 is 387.9 kilojoule per kg. Let us take the entropy value also, because we will be requiring to find out S1, entropy at S1. So let us take S1 dash entropy also. Let us take the entropy at 1 dash at minus 18 degrees centigrade. The vapor entropy is 1.7399. So since it is required for further calculations, similarly S1 dash is equal to Sg at T1 dash equal to minus 18 degrees centigrade. Therefore, S1 dash is equal to 1.7399 kilojoule per kg. So both these are from R134A table at minus 18 degree centigrade. 1.7399. Let me check the value. 1.7399. So that is, since 1 dash is lying on saturated vapor curve, directly we can read Sg value and Hg value from the table corresponding to minus 18 degree centigrade. Now let us calculate. Now let this be equation number 1. Let this be equation number 1. Substitute the values of H1 dash, which you have found from the table. Cp of vapor value is here. T1 and T1 dash are given in the problem. So therefore, in equation 1, H1 is equal to H1 dash is 387.89 plus Cp of vapor is 0.827 into delta T. T1 minus T1 dash. T1 minus, so minus 10 minus of, let me put as minus of minus 18, that will become plus 18. When we calculate H1 is, it comes to, H1 is 394.5 kilojoule per kg. 394.5 kilojoule per kg. Now we will consider the process 1 to 2. We consider the process 1 to 2. 1 to 2 is isentropic compression. S1 is equal to S2. We will write the formula for S2 minus S2 dash equal to Cp of vapor into ln of T2 by T2 dash. We need to find out the temperature at T2. So I will write a similar formula connecting state point 1 and 1 dash, that is S1 minus S1 dash is equal to Cp of vapor into ln of T1 by T1 dash, and use with the help of that one I will find out S1, because S1 condition state point 1 is in superheated condition, for which the entropy cannot be taken from the table directly. However, we can take the entropy only for state point 1 dash and state point 2 dash. So if you see the diagram, 1 dash is lying on the saturated curve, 2 dash is also lying on the saturated curve. But if I want to find out the entropy at 1, I have to use that relation. So S1 minus, now to find entropy at state point 1. So S1 minus S1 dash is equal to Cp of vapor into ln of T1 by T1 dash. Where Cp of vapor, since we know T1 and T1 dash, Cp of vapor should be taken at the average of T1 and T1 dash, which we have already found. So that is equal to minus 10 minus 18 by 2. That is equal to minus 14 degrees centigrade. This is what we have found here. Cp of vapor is equal to, it is the same value, 0.827 kilojoule per kg Kelvin from R134A table. So S1 minus S1 dash is equal to Cp of vapor into ln of T1 by T1 dash. So using this, we can find out the entropy at state point 1. So this will be equation number 2. So now if you see this one, Cp of vapor is known, T1 is known, given, T1 dash is given, S1 dash we have found here, this is S1 dash. So substitute the values of, let me write it in the next slide. Substitute the values of S1 dash, Cp of vapor, T1 dash in equation number 2. So equation number 2 is this equation, S1. Let us rearrange this equation and write, or let it be as it is. S1 minus, the value of S1 dash is 1.7, this is the value of S1 dash, 1.7399, that is equal to Cp of vapor is 0.827 into ln of T1 by T1 dash. Since the temperature is in the ratio, we have to substitute in Kelvin. T1 is minus 10, so plus 273. T1 dash is minus 18 plus 273. So that is in Kelvin, it will be 263 and 255. So solving this one, we will get S1 is equal to 1.7643 kilojoule per kg Kelvin. So we have found out enthalpy at state point 1, entropy also state point 1. Now I will use this entropy at state point 1 to write S1 equal to S2. This will be the entropy at state point 2, because 1 to 2 is isentropic process. Since 1 to 2 is isentropic process, therefore entropy at 1 is equal to entropy at 2. That is, S2 is also 1.7643 kilojoule per kg Kelvin. So let us go to the, so if you see this one, see this is 1.76, I think 1.7643. S2 dash, this is, let me check the value. just one 1.7 point. Let me check the. I think this is 1.7643. 1.7643. Correct. There is one. Now let us go to state 2. Then we will calculate T2. Once we find T2, we can find out the superheated enthalpy at H2. So process 1 to 2 is isentropic compression. So S1 is equal to S2. So S2 minus S2 dash is equal to Cp of vapor into ln of, so state 2. This is state 2. S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. Here T2 is unknown. Okay, T2 is unknown. We know only this temperature. So therefore Cp value is at T2 dash. What is it? Let us see the temperature at T2 dash. T2 dash is condensate temperature 32. That is equal to 32 degrees centigrade. Therefore, Cp of vapor is equal to, let us go to this refrigerant table, corresponding to 32, Cp of vapor is 1.058. 1.058 kilojoule per kg Kelvin from R134A table. 134A table. So now Cp of vapor is also known. S2 dash can be easily found because S2 0.2 dash is lying on the saturated vapor line. So S2 dash is equal to, S2 dash is, let this be equation number 3. S2 dash is equal to vapor entropy at T2 dash, which is equal to 32 degrees centigrade. Therefore, value of S2 dash is equal to, corresponding to 32 degrees centigrade, vapor entropy 1.7142. 1.7142. 7142 kilojoule per kg Kelvin. Kilojoule per kg Kelvin. Substitute the values of, now this we have found S2 dash, so the only unknown is S2. Substitute the values of S2 dash, Cp of vapor, T2 dash in equation 3. In equation 3. So S2 minus S2 dash is 1.7142. Cp of vapor is 1.058 into ln of, temperature should be substituted in Kelvin, T2 by T2 dash. T2 by T2 dash. T2 is 32. So 32 plus 273. T2 dash is, T2 dash is 32. Temperature T2 is, we have to find out. T2 is unknown. T2 dash is 32. That is 32 plus 273. Sorry, one small correction. S2 is nothing but S1. S2 is nothing but S1. So we can substitute here. Sorry for the error. S2 is known. The only unknown is T2. We'll substitute the value 1.7643. So we get, solving this one, we get T2 is equal to, you will get around 320. T2 is equal to 320.3. 320.3 Kelvin, which is equal to 47.3 degrees centigrade. 47.3 degree centigrade. I have found the value of T2. I think we have stopped it here. T2 is 47.3 degrees centigrade. There is one topographical mistake. In the previous lecture, this portion, it was showing 1.7633. Actually, if we see the value of S2, if you see the value of S2, which is equal to S1, that is 1.7643. It is not 1.7633. So there is one small typing error, so which I have rectified. So substituting the values, we are getting the value T2 as 47.3 degree centigrade. 47.3 degree centigrade. So now we know the value of T2. We can find out the enthalpy at state point 2. Enthalpy at state point 2. That is superheated enthalpy. Superheated enthalpy. If you look at this diagram, superheated enthalpy is equal to saturated enthalpy 2 dash, which we can take it from the table, plus Cp of vapor into Cp of vapor into delta T, T2 minus T2 dash, T2 minus T2 dash, to find H2, H2 is equal to H2 dash plus Cp of vapor into delta T. Delta T is T2 minus T2 dash. T2 dash temperature we know, that is condenser temperature. T2 just now we have found out. So let this be equation number 4. Equation number 4. Cp of vapor to be evaluated at the average temperature of T2 plus T2 dash. T2 plus T2 dash by 2. So T2 is 32. T2 dash is 40. Sorry. T2 dash is 32. T2 is just now we have found. Let go. I think towards the end of the previous lecture. T2 is 47.3. 47.3. 47.3 plus T2 dash is 32 divided by 2. So this is approximately 80 degree, 80 by 2. So Cp of vapor to be evaluated at 40 degree centigrade. So this is 32 plus 47.3 is 79.3. So I have taken as 80 by 2, 40 degree centigrade. So this is Cp of vapor is equal to corresponding to 40. 40 is here. Cp of vapor is 1.120. 1.120 kilojoule per kg Kelvin from R134A table. From R134A table. So now Cp of vapor is also known. Substitute the values of, but before substituting the value, we need to find out H2 dash. H2 dash is equal to, it is vapor enthalpy corresponding to temperature T2 dash. T2 dash is nothing but condenser temperature. Let us go to the diagram. T2 dash is equal to T3, which is equal to T2 dash is equal to T3, which is the condenser temperature. If you see here, T2 dash equal to T3, this is equal to condenser temperature. That is 32 degree centigrade. 32 degree centigrade. So H2 dash is equal to, corresponding to 32 degree centigrade, vapor enthalpy is 415.9. 415.9. 415.9 kilojoule per kg from R134A table. From R134A table. Let us check from H2 dash is equal to 415.9 kilojoule per kg. Okay, now I will substitute the values and find out H2. Substitute the values of, so now we have found H2 dash. So we can find out H2. H2 dash, Cp of vapor, T2 dash in equation 4. Therefore, H2 is equal to, H2 dash is, just now we have found 415.9 plus Cp of vapor is 1.12 into delta T, T2 minus T2 dash. T2 is 47.3, T2 dash is 32, that is condenser temperature. H2 is equal to 433.1 kilojoule per kg. 433.1 kilojoule per kg. So now we have found the enthalpy at 2. So we have determined the properties at state point 1 dash, 1, 2 dash, 2. Now we are to find out the properties on towards the liquid region, that is H3, which will be equal to H4, because 3 to 4 is isenthalpic process, that is without considering subcooling, and H3 dash we have to find out, that will be equal to H4 dash, isenthalpic process, that is considering subcooling. So now let us move to state point 3. State 3. So H3 is equal to liquid enthalpy at temperature T3. T3 is nothing but condenser temperature, that is 32 degrees centigrade. So if we see the value, H3 is equal to, corresponding to 32, liquid enthalpy 244.55. 244.55 kilojoule per kg from R134A table. From R134A table. Since the problem involves, apart from superheating, subcooling also, we need to find out the enthalpy at 3 dash. Enthalpy at 3 dash. So this procedure will be the same, similar to the previous problem. Previous one lecture problem where we have solved a problem based on subcooling. So this will be equal to H4 also. Anyway, now we need to find out H3 dash. To find H3 dash. H3 dash, state point 3 dash is lying on the subcooled region. So subcooled enthalpy is equal to saturated enthalpy, that is liquid enthalpy, minus Cp of liquid, not vapor, into delta T. Delta T is the degree of subcooling, that is T3 minus T3 dash. T3 minus T3 dash. This is condenser temperature. This is the liquid refrigerant is subcooled to 26 degrees centigrade, which is given in the problem. So this is T3 dash, subcooled to, it is subcooled to 26 degrees, that is T3 dash. So this is T3 dash is equal to 26 degrees centigrade. And of course, this is 32 degree centigrade. So we are in state 3. H3 dash equal to H3 minus Cp of liquid and T3 minus T3 dash. Once we find the Cp of liquid for the average of the temperatures T3 and T3 dash, H3 we have just taken from the table, we can find out H3 dash. So here Cp of liquid is equal to, at average of T3 plus T3 dash by 2. T3 is 32, T3 dash is 26 divided by 2. So that is equal to 58 by 2, that is 29 degrees centigrade. So Cp of liquid is equal to 28, temperature 28 and 30 are given. We need to find out for 29. So we have to take the average. So this is Cp of liquid. And the last one is Cp of vapor. So we have to take the average of these two, like how we took for the problem which involves only subcooling. It will be 1.4142. The average value will be 1.4142 at 29 degrees centigrade from R134A table. Let us take this as equation number 5. I think the previous equation is equation number 4. Equation 4. Now H3 is known. Cp of liquid we have found. T3, T3 are given. So let us substitute the values. Substitute the values of H3, Cp of liquid, T3, T3 dash in equation 5. In equation 5. So therefore H3 dash is equal to H3 is 244.55. Cp of liquid is, let me check the value, 1.4142. I think that is the average. Cp 442. Cp of liquid is 1.442. Small correction, it is 1.442. 442. So 1.442 into delta T, that is 32 minus 26. So if we calculate the enthalpy, the subcooled state, that is at 3 dash, will be equal to 235.8 kilojoule per kg. Kilojoule per kg. This will be equal to H4 dash. Since 3 dash to 4 dash is isenthalpic process, H3 dash is equal to H4 dash. H3 dash is equal to H4 dash. Okay, so that's what we have found here. Now we have found all the enthalpies. 1 dash with the help of 1 dash we have found 1. Then we have found T2 temperature. Without T2 temperature we cannot find the superheated enthalpy. For determining the superheated enthalpy, we should know the enthalpy at saturated condition 2 dash, which we have taken from the table. State point 3 is lying on the saturated liquid line. So H3 is HF, that is liquid enthalpy corresponding to condenser temperature. And this is H3 will be equal to H4 if we don't consider, without subcooling means the refrigerating effect is from here, that is 1 to 4. Because we are considering subcooling, it is up to 4 dash. It is up to 4 dash. So H3 dash is equal to H4 dash. And the subcooling process is shown in with a dotted line. So now let us calculate the parameters, rate of heat removal, that is H1 to H4 dash. Enthalpy at the outlet of the evaporator or inlet to the compressor to the up to 4 dash. Not it is 4, it is H4 dash. So similarly here also m dot, it is m dot r. Even in the given data also I think m dot, this is m dot r. Here also m dot r. So m dot r into H1 minus H4 dash. Evaporator heat load is equal to refrigerant mass flow rate into H1 minus H4 dash. 0.05 into H1 is, H1 we have calculated 394.5 kilojoule per kg. 394.5 kilojoule per kg. Minus H4 dash, we have calculated, H4 dash is nothing but H3 dash, which we have calculated little ago, that is 235.8. 235.8. So the cooling capacity or the evaporator heat load comes to 7.93 kilowatt. 7.93 kilowatt. 7.93 kilowatt. Let us calculate the work of compression. Work of compression. So that is equal to m dot r into H2 minus H1. So if you go to the TS diagram, this is the compression process. The refrigerant is compressed from state point 1 to state point 2. It is not from state point 1 dash, it is from 1 to 2. This is superheating, which is given in the problem. The superheating temperature, this is T1 is minus 10. This is given, this temperature is given in the problem, which is minus 10 degree centigrade. Minus 10 degree centigrade. So let us substitute the values. So m dot r is 0.05. H2 is here. H2 is 433.1. 433.1 minus H1 is this value 394.5. We get the work of compression as 1.93 kilowatt. 1.93 kilowatt. Second part of the question is condenser heat load. How much heat is rejected to the environment? That is equal to m dot r into H2 minus H3 dash. H2 minus H3 dash. Without subcooling, the formula for condenser heat load is H2 minus H3. But if when subcooling is there, we need to take the subcooled state 3 dash. That is H2 minus H3 dash. So let me explain again with the diagram. See, without subcooling, the condenser heat load is H2 minus H3. With subcooling, it is from 2 to 3 dash. Because the subcooling takes part on the lower part of the condenser. As I explained in one of the lecture, some additional heat transfer surface area would be provided in the condenser for the subcooling process to take place. Let me substitute the values. 0.05 into H2 is 433.1. H3 dash is nothing but H3 dash we have calculated. H3 dash we have calculated. This is H3 dash, which is equal to H4 dash 235.8. 235.8. So this is the condenser heat load comes to 9.86 kilowatt. The COP of the system is ratio of cooling capacity or refrigerating effect divided by to the work of compression. 7.93 divided by 1.93. So COP comes to 4.10. 4.14. Let us do the energy balance. Energy. So QE plus WCO is equal to 7.93 plus 1.93. This will be equal to 9.86 kilowatts, which is equal to the condenser load. So that's what we are getting. It's a perfect energy balance. So with this, let me conclude lecture number 8. Thank you.